All right, so looking at this bell work, what everyone was able to get, since everyone answered C or D, oops, I'm not writing, I am. Everyone knew that you want a big sample size. The question is, do we want a smaller or bigger significance level? And as a reminder, since the sample sizes are basically fixed, I'm going to move this one over just a little bit so there's more overlap. All right, so if your significance level is right here, and you move it over just a little bit to make it a 0.1 rather than 0.05, then what you get is the shift in power. So here's your power with a 0.05. And then when we shift that over to the left, meaning we have a higher significance level, then that allows us to more easily reject the null. So the power of our test has increased. So we actually want a higher significance level. Does that make sense?
Yeah.
Question?
Well, I'm just confused because you went from, shouldn't they be reversed if the 0.05 is on the left and the 0.1 is on the right? And you like,
so no, that's a good question. And the 0.05 and the 0.1 represents the tail area. So this one on the left is our null hypothesis. Or not the null hypothesis, but the null proportion. All right, so that means that we have a 10% area under that curve right there. So if anything, it only has a 10% chance of happening. It happens. We say that's random enough that we reject the null hypothesis. We can more easily reject it. If it was 0.05, then we're only dealing with this area. And it has to be a more extreme value for us to reject the null hypothesis. So yeah, making it easier to reject the null makes it more powerful. All right. All right, the first thing we need to start off with today is progress, the progress that we have made. All right, maybe it seemed like a while since we've done this, I don't know. But look at this, we started at Lee's Ferry, we're working our way down this river. We've made it all the way to Indian Canyon. And I want to remind you, we're not making it to the end, we're making it to Separation Canyon. And there's a nice smooth float down the end while we do some review of everything. So 277 is going to be our last day of school year, but this is the end of our new content that we have to learn. So we're Indian Canyon. It's just kind of a random place maybe for us to be at. And so we don't have to spend too long with this, but it's good to see where we've made it to. This is definitely where the canyon takes on a different shape. And we're in the western part of the canyon where we get the Escalante bench rather than the Tonto bench. All right, you can see what's going on there. It's just a lovely river scene. Okay, well, wasn't that fun? Let's go back to our lesson. Let me get back into this. So here's what we're doing today. We're going to be looking at chapter 26, which is dealing with your chi-square test. If you guys already skimmed through, these tests are, I think they're actually kind of interesting tests. You might agree or disagree, but let's kind of approach it from this perspective. If I gave you a list of 900 data points that could take on any numerical value, so that means it could be a single digit number, it could be decimals, it could be 247 or 8 million, right? So it could be any value. So how many of those data points would you expect to have a leading number of 1? This is a question you're allowed to answer. 100. That's a fair assumption, right? And I picked 900 so that we had a nice round number to work with. So there's 9 leading. You can't lead with a 0. So leading with 1 through 9, 100 of them, right? So this is kind of where we anyways, if we're looking at how many would have a leading number of 2 or 3, you'd probably expect 100 of each. So in the 30s, Frank Benford was looking at a number of data sets and found that the leading number for each data point was not distributed proportionally. While we might expect each number to be the leading number 1/9 of the time, that's not actually what happens. And this is there's a distribution that we call, part of what we call Benford's law. And anyways, this is what it is. The number one, when you're dealing with, and I'll come back to this point, but when you're dealing with a data set with a lot of different orders of magnitude, if it's all between 1 and 100, it doesn't work this way. But if it can go between, 0 and infinity, and you pick any random numbers, then approximately 30.1% of them will start with a 1, 17.6 are going to start with a 2, and so on. All right, and maybe we can get into the reasons why. So you can notice that 9 is only a leading number about 5% of the time. And anyways, there are logical reasons for it. And the distribution is a result of mathematical model, but repeated testing of this has found this to be true of many data sets. Okay, and this is what I was saying. It has to be a lot of different orders of magnitude. So hundreds, thousands, 10,000s, and so on. And we're going to look at a data set to see if this distribution breakdown holds. We're going to be looking at the 58 tallest buildings in the world with the data already summarized. And here we go. And this is actually, I looked up this and I found these numbers myself just because I just wanted to see if this worked. So I did this last semester, so it's been a while since I've looked at it. But if you look at the tallest buildings in the world, what is this? The tallest 33, 47, 52, 53, 58. The tallest 58 buildings in the world. This is not saying how tall they are, but the leading number is 1 for 24 of those and so on down the line. So anyways, oops. What's going on? There we are. So does this, we don't have the actual probability breakdown. We're going to see that in a second. But this is what the distribution should be if Benford's law is true for tallest buildings. Does it seem like it fits that? You don't have to sit there and do the math to figure it out, but does it seem like it fits pretty closely? All right. Yeah. Yeah.
What are like the benefits of like having something like the data like this? Or like doing like deconstructing it, I guess is what. Yeah.
The benefits of this, well, actually, it's funny that you ask. Like, are you saying with specifically with Benford's law?
Yeah.
Okay, it is funny. First of all, you can use this to detect if there's fraud that's happening, because a natural, and this is, I actually learned about Benford's law about this time last semester because it came up in the wake of the election, because there were claims that there was election fraud going on because different precincts, voting precincts, the claim was that they should all follow, it should follow Benford's law, right? So if you have, and they just looked at Chicago, I think. If there's 1,000 precincts in Chicago, voting precincts, then you should see 30.1% of them end up with, as far as number of votes for Biden, let's say, 30.1% should have a leading number of 1, and so on. And the problem, is that making sense?
Yeah.
Well, why would it vote have
Well, it might be, supposedly if you had a, yeah, so maybe it'd be like 12,324 votes for Biden here, and then 1,252 in another precinct. So just the leading number, it doesn't matter exactly how many votes there were.
I was just confused. I thought you were from individual votes.
Oh, yeah.
I was like,
Yeah, that's what we're talking, yeah, votes for. Now, the problem with this being used as, and the thing is, it actually broke down to what you would expect. When you look at the precinct votes, it broke down like 11.1%, stuff like that. It didn't follow Benford's law. And so people were saying, therefore, there was election fraud. The problem with that thinking is that Benford's law applies to data sets with lots of orders of magnitude. And voting precincts, on the contrary, are all set up to be about the same size. You want to have the same volunteer, like election workers, to be working with the same amount of votes. So we weren't dealing with a precinct that had 100 voters and then another one with 10,000 voters. We're dealing with precincts that were all, I'm making something up, all about 1,000 voters, right? So you just have 1,000 over and over and over again. So with that, because you're not getting a lot of different orders of magnitude, Benford's law doesn't apply. And if we want to get into the reasons behind Benford's law without getting too mathematical with it, have you ever seen a log table, like a logarithmic chart, where, and I'm just going to superimpose it on top of this rather than come up with something new, but logarithmic scale, like if here's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Dang it, I just erased everything that I did. So anyways, if you start at 0, logarithmically, if you think about what percent growth is required to move up from 0 to 10, or sorry, from 1 to 10, what kind of growth is required? So these just get tighter and tighter, logarithmically speaking. All right, does that kind of, you can kind of see what I'm trying to get at. So jumping from 1, which would be right here, and I'm going to say this is 10, 20, 30, 40, 50. Anyways, those are all with the 0 at the end. So if I went from 1 to 10, that's a 10-fold growth. But if I went from 11 to 20, it's the same gap, right? I'm still just going up 9. But proportional to where it started from, it's a lower jump, right? It's a 9/11ths jump, right? And then if I went from 21 up to 30, then that's just a jump of 9 compared to 21. So that's even less, proportionally speaking, of a jump. And finally, when you get up to 91, jumping up to 100, proportional to the starting value, a jump of 9 isn't that big of a jump. And so it's a kind of a, there's a lot of interesting stuff dealing with logarithms and exponential growth and all this fun stuff, that it's harder to jump from 0 to 1 than it is from 9 to 10. And when you jump up to 9 to 10, then you jumped up to a new order of magnitude. And then it's harder to jump from that next order of magnitude 1 to the 2, then so on, just as far as proportional growth. And so this is why we're going off a little tangent, but it's kind of fun stuff. When you are changing the volume on your, whatever you're listening to, you're not going up from like 30 decibels to 40 decibels. Well, right, let me change what I'm saying. 30 decibels to 40 decibels and then 40 to 50. This is not a linear growth. This is actually a logarithmic growth. So 30 to 40, 40 to 50, that's a lot, like it's exponentially louder, because to recognize a difference, our ears need to hear an exponential growth, not just a linear growth in the volume. Same thing with your Richter scale when you're dealing with earthquakes. So and this one's maybe a little bit easier to explain, but if you jump from my son was asking about earthquakes the other day. He was saying, what if there's like a 13.0, right, earthquake? Well, jumping from a 5 to 6 earthquake the 6 is 10 times more powerful than the 5. And then the 7 is 10 times more powerful than the 6, and so on. So you can see, so the most powerful earthquake that we've ever experienced is a 9.5 that's ever been recorded, which is huge, right? But and if you're like, oh, well, just jumping up to a 10 isn't that big of a deal. Well, that's exponential growth. That's going up by a factor of, I don't know what it is to go from 9.5 to 10, but it's going to be multiple times more powerful. And so therefore, if we did ever see a 10.0 jumping from 10 to 11, the next earthquake would have to be 10 times more powerful than the 10. So that's why there is kind of a logical limit to how big an earthquake can be. Otherwise, we're tearing the earth apart. So I don't know what the theoretical limit is, but you're not going to see just a 13 earthquake.
Let's find out. You think your son will go on to
I did read a website once, and we're really getting far afield here, but we'll still do what we're supposed to. I did see your website one time. I'm recording all this, by the way, so if you want to not learn statistics later, you can watch this again.
I can't wait to go back and watch it.
Yeah, there's an article, it came out years and years ago, where there's a guy who, I don't know, super smart guy. He was trying to figure out how could you destroy the earth? Not how could you kill everything living on earth, because that's easy to do. We do that ourselves. But how could you physically destroy the earth? And he came up with all kinds of different possibilities where, you know, could we like steer the earth toward the sun so that we can destroy it? Can we like try and find the harmonic resonance of the earth so that, you know, if you get the harmonic resonance of a glass, you can get it to shatter?
Yeah.
Can we find the harmonic resonance of the earth so that we can get it to shatter? And long story short, he's like, it's very hard to destroy a planet. And with that, maybe we should get back to learning about chi-square tests.
I thought that was like very anticlimactic.
I know.
I didn't know.
Oh no, not right now.
I thought he was gonna find some like dope way to like destroy the earth. But then long story short,
we can, we'll have to ponder that question a little more. Sorry, that was anticlimactic, but here, let's look at this again. Let's remember our original scenario, which is that we have a presumed distribution of leading numbers. Here's the actual one. I did the math for you. Let's not take our time with that. So the actual distribution is this. 41.5% had a leading number of 1, down to 1.7% at the bottom. So we can see it's not perfect. And the question that we need to ask ourselves is it close enough that we can assume that Benford's law still applies? And luckily, I mean, the whole point of the test we're going to learn today is we can determine if it is close enough. But I mean, I'll let you guys answer. Is this close enough that we say, yes, this follows Benford's law? Or is it far enough away you're like, I think it doesn't follow Benford's law? And the good thing about this right now, it's just speculation. And
I'm gonna guess it does
you're going to guess that it does follow Benford's law.
Yes.
Just to be, so we have a
Of course you
a yes and a no. Okay, so we have 2 no's and 1 yes. And uh-oh. All right, we're going to use a chi-square test to figure out if it does apply. So this, well, it says, it sure seems like this data set complies. Well, apparently I thought so. But we want to check more accurately to see if it really holds true under statistical scrutiny. So we're going to use a chi-square statistic. And this is right from your AP formula sheet. That's like, I say that every single day, right? Don't I? And this is found right here. You're getting to know more and more about what all this stuff means. So at the very bottom, you can see that. Luckily, we'll kind of talk about in the long run what you need to know, what you need to show for chi-square tests. So actually, let me go back to make sure we see the formula. So we have the observed value minus the expected squared, and then we're going to divide that by the expected. And since we do this for each data point, we're then going to get the sum of the total. And I will tell you right now, this, anytime you see a sigma, this means it's going to be a bunch of work if you try and do it by hand. If you have 100 data points, you have to do 100 calculations and then add it all together. So this is my long way of saying, we do not do the chi-square test by hand. All right, and that's a good thing to know. We're going to do the first one by hand, but then after that, we will not. So here is how we're going to do this. You can see our observed minus expected. We're going to then square it, and then we're going to divide it by the expected, and we're going to add it all up at the bottom to get our chi-square value. All right. I went ahead and calculated the expected amounts based on if there are 58 buildings, how many would we expect to have a leading value of 1 if it follows Benford's law? And now we can do some subtraction. So you can start filling in this table with values. We're just doing observed minus expected, which in this case is going to be 6.5. And I'm just going to leave it here. You guys can start filling in the table. So we've gotten all of our differences. And one thing I misspoke a second ago, it's not 100 data points. If we had 100 categories. So right now we have 9 categories. We had 58 data points, but we had 9 categories. If we had like 100 categories, then we'd have to calculate 100 times. But regardless, we still don't do this by hand except for this one time. Now we can take this and we can square it. 6.5 squared. I know you know how to do squaring, but I'll just fill in the first one. 6.5 squared, just so I can say I contributed, is 42.25. All right, and fill in the rest of that. Okay. So now well, and I misspoke a second ago. The 2080 rule I just talked about. That's not exactly an example of logarithms. That's an example of a power law, which is a different kind of, what's the word? It's a different kind of formula, different kind of equation. We'll get into that a little later. So now we can take these values and we want to divide it by the expected. So in this particular row for number 1, 42.25 is the observed minus expected squared. When I divide by 17.5, I get 2.414. We can go to thousandths here. So go ahead and calculate all that. And let's go from there. So we calculated this observed minus expected squared divided by expected. And we get all these, some of them are big, some of them are small. We can add this up. And so we just want to take this column and add it up. I think one time we calculated our standard deviation by hand. And it's the same kind of calculation we're doing here, but you can just sum that up and put the number down at the bottom. Okay, so when we add this up, we get 8.214. And throughout this entire time, this really hasn't meant much, right? So it's big deal. So we're getting this number. And in fact, I'm going to go ahead and we have the 8.214. Let's see if that's, oh, I got 8.82. So there might have been a calculation error along the way. So I know it's 8.82, but we're in the ballpark with the 8.214, all right? But let's just correct it to say there is an 8, it should have been 8.82. Let me clear off all this work we did. And like I said, in the future, we don't need to do any guesswork. And when you have to do 50 calculations, it's likely you're going to make a small error along the way. Luckily, the calculator does all that for us and we don't run into those problems. What does this even mean? So we're going to be learning about 3 different chi-square tests, but today we're going to be using the chi-square for what we call the chi-square goodness of fit test. And it is the chi-square, not the chi-square or the chi-square. It's the chi-square. All right.
I don't know why, but that kind of like, it sounds very made up. Goodness of fit.
Well, we'll see why it's called the goodness of fit test. And it is very made up by people, but it works out mathematically. Well, that's a question. There's another philosophical question we're getting into is math inherent and we're just discovering it, or is math invented by people? What do you guys think?
Numbers are inherent. I think there's laws to numbers.
Yeah.
You know what I'm saying?
Because there's some arguments that even like animals recognize numbers.
Yeah. Really?
I mean, animals besides humans. Yeah. And not recognizing numbers as far as like recognizing the number 1 or 2, but it's recognizing there are 2 things there.
Yeah.
All right, so let's get back to chi. We're just jumping away from chi-square and back into it just repeatedly today, but it's all good. So the chi-square test is a test of whether the distribution of counts in one categorical variable matches the distribution predicted by a model. So in a chi-square goodness of fit test, the expected counts come from the predicting model, and the test finds a p-value from a chi-square model with n minus 1 degrees of freedom, where n is the number of categories in the categorical variable. I think I found this description of it, maybe from the textbook, and copied it down. I think this is, but anyways, this has all the essential information in it. But we're going to break it down more. So when you look at this in your calculator, you're going to see GOF, goodness of fit. Okay, we are dealing with categorical variables with this. So therefore, we're dealing with counts. So at the beginning, I gave you a percent breakdown. Like if I go back to the beginning, if you remember, Benford's law said 30.1% all the way down to about 5%. But we can't deal with percents when we're working with chi-square. Now we need to work with counts, the expected counts. And this repeats what I said before. Anytime you see a sigma, that means it's going to be very cumbersome to do that math by hand. So we're not going to do it by hand. So any other inference test we've done before requires only a few inputs, but this requires a lot. So if we're good with all those kind of concepts there, now we're going to figure out how we can interpret this chi-square value that we got. We need to have some hypotheses. And here's the first hypothesis. And, it's that the claimed distribution is true. Now these hypotheses, we actually don't write in mathematical formulation. We just write it as a phrase. So the null hypothesis is that the claimed distribution is true, or in other words, Benford's law is true for this data set. And then the alternative hypothesis is that the claimed distribution is not true and Benford's law doesn't apply. So the null hypothesis is always the no change. And that means if there's a claimed distribution, we're going to claim that, yes, it does match that. Now, sometimes the assumed distribution is a flat distribution. So the expected amount is going to be the same for each category. So if you're going to predict the expected amount of the expected count of each color in a bag of M&Ms, you'd expect to get about the same amount for each color. And I believe that is a flat distribution. There's no extra blue or red or other color. Now, we are going to be looking at the table. In fact, if you have your formula sheet, or your AP formula sheet, the very back page, now you get introduced to this fun thing. On the back, it looks kind of like tables A and B, well, table B specifically, where it gives you degrees of freedom on the side. So we're going to have to work with degrees of freedom still, but the degrees of freedom is going to be the number of categories minus 1, not the number of data points. We had 58 buildings in our data set, but there are only 9 categories, which was the leading number. So you guys with me on this? So if we have the number of categories is 9, our degrees of freedom is 8. There it is.
So it's always 8 for this,
No, it's not always 8 because, yeah. So in a different data set, let me give you guys,
they're telling you 9,
in this data set, we're dealing with leading numbers, but that's a good question because I could give you another set, maybe just to give it a little more context of how this is useful. I think that, that of all the ice cream flavor, of these 3 ice cream flavors, chocolate, vanilla, strawberry, CVS. Let's go with, no, let's just call that good. I think 40% like chocolate best, 40% like vanilla best, and 20% like strawberry best. That's my claimed distribution. And then I took a sample of people, 100 people, and it broke down a certain way. Now my number of categories for this data set is going to be 3. So my degrees of freedom will be 2. So just with our first example, there were 9 categories, so we had 8 degrees of freedom. Now in a different situation altogether, I have 3 categories, so 2 degrees of freedom.
what were our 9 categories for?
Just the leading numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, and it was a category. I know it sounds quantitative, but I mean, if the building was 1,352 feet tall, then it went into the category of 1. All right. So we can have a different number of categories for lots of different goodness of fit scenarios. So here are data points. We're going to pick a significance level. This is a hypothesis test. And the hypothesis is that the claim distribution is either true or not true. And this is what we're going to do. I already kind of drew your attention to the last page of your formula sheet, but now we can see our chi-square critical values. And going along the row for 8 degrees of freedom, we want to see where our chi-square value lands. Now, if I look at 8 degrees of freedom, and so I'll put this up on the screen. So 8 is right here. Okay. It's right in the middle right there. And notice it starts at like 10 point something. And as you go from left to right, it gets bigger and bigger. So it starts at 10, and by the time you get all the way over to the other side, it's 27.87. So way over here, 27.87. It also gets bigger from top to bottom. So as your degrees of freedom goes up, so do your critical values. And that's because, remember, this is a sum of a lot of different categories. So this is going to get bigger naturally. But is it big enough to be critical? And we don't need to care about where these numbers come from. But it does come from a chi-square distribution and where the critical value point is. So if we say that we're dealing with a 8 degrees of freedom, up at the top is your tail probability. So let me kind of explain what that means. Let me just clarify something. This is, okay, you can see okay, how do I explain this? A chi-square distribution is a very weird shape. And if it's a degree of freedom of 2, it actually just is like a curve coming down like this. But with the bigger ones, it kind of creates this weird curve. If it gets big enough, it actually starts looking normal again. But at this level, yeah, you have kind of this weird shape to it, a skewed right distribution. And there is a way of calculating where your critical values are. So what we're saying with this 8 degrees of freedom with an 8.82 critical value, or chi-square value, is that this is all the way off the chart this way, because it starts at 10, works its way up to 27. So that means 8 is actually going to be over here somewhere. And how do we interpret that? What that means is that there is greater than a 25% probability of getting this result, assuming the null hypothesis is true. So if we set our significance level at 0.05, which is right here, I believe, if I'm pointing to it correctly, one of these two, then we would need to get a chi-square value bigger than this in order for us to reject the null hypothesis. And I'm still not sure that's making a lot of sense. But, oh, I had it on screen. I could have just done this a little more simply. All right, so let's kind of see if I can say all this again, but in a clear way. So since my 10.22 is right here, my chi-square value is 8.82. So over the totality of all my categories, this is the total deviation away from what I expected it to be, 8.82. If these numbers were really far off from what we expected, then this sum would be really big, right? Because whenever I did an observed minus an expected value and then squared it, if this observed value right here was way different from the expected, then I'm going to square this thing. I'm going to get a huge deviation from what I expected. This number is going to get big. Even when I divide by the expected, it will be a pretty big contribution to my chi-square. So if I expected 17.5 for the count for my first category, we got 24, I believe. But if we had gotten like 34, imagine how different that would be as far as the distribution goes. That would change our statistic a great deal, right? So it would make our chi-square value even bigger. Is this making sense mathematically? Okay, I just want to make sure it's clear. If the observed values are far different from the expected values, you're going to get a bigger chi-square. That's the takeaway. Okay, so if we're good with that, to interpret this again, the 8.82 means that it's going to live somewhere over to the left off of this chart. My significance level is 0.05. So to reject the null hypothesis, I would want this value to be, to reject it, my chi-square would have to be greater than or equal to 15.51. Does that make sense now? So any value greater than 15.51 would be grounds for me to reject the null hypothesis. Because especially if we get over here like 22 range, there's only a 0.005 chance of that happening by random chance if the claimed distribution is true. Okay. I'm going to pause there and let everyone breathe, see if there are questions that are popping up. Okay. So what does this mean? The fact that our 0.88 or 8.82 is off the chart over to the left. I kind of summarize it right here, I believe. It turns out that our value is off the table to the left, which means there's a greater than 25% probability of getting results like this by chance alone, assuming the null hypothesis is true. Our p-value is greater than 0.25. Therefore, we fail to reject the null hypothesis because our p-value of 0.25 at a minimum is greater than our significance level of 0.05. So even building heights follow Binford's law. We failed to reject it, so our null hypothesis remains true. Okay. Questions here? All right. To find an even more accurate answer and to save time, your calculator can perform this test for you. So we want to put all the observed values in one list and the expected values in another. And then we can do this chi-square goodness of fit test. It actually shows up in your calculator. So in the interface, you want to select the appropriate list for observed and expected and put in the correct degrees of freedom. And with a table, we could only get accurate enough to say it was greater than 25% probability. But we can find the true p-value. So you will need to see that table again. I want you guys to actually practice with using your calculator on this. It's going to be faster if I jump to somewhere over here. This one, there it is. Here's your observed values. Put that in one of your lists. Here's your expected. And then I will guide you back to the chi-square test if you forgot how to get to it. But it's under stat and tests. What is the true p-value if you've had the chance to do your goodness of fit? And if you haven't yet, then just look right here. You can find it by going stat, tests, goodness of fit test, which is option D. And then you just need to select your two lists and put in 8 degrees of freedom. So feel free to write down the p-value that you found. There it is, 0.358. Okay, what does this 0.358 means? It means there's a 35.8% probability of getting the results we did, assuming the null hypothesis is true. That's pretty likely, right? We only reject the null if it's an incredibly unlikely outcome. So with this, we say we failed to reject the null hypothesis. And I wanted to draw your attention to this output on your calculator, where if you look right here, Okay, it's working for me, I think. Is it working? Okay, let me try this again. No, it's working. I'm sorry. Okay, so you have your outputs right here. Sorry, I'm trying to do two things at once. You have your chi-square at the top, which we calculated 8.82. You have your p-value, your degrees of freedom, but then down at the bottom, the CN, that's your contributions. So it's going to show you from your first category, how much did that contribute to your chi-square statistic? The 2.41, that's a big contributor. But you move to the next one, is 0.141. That was not a big contributor. You keep going over, and I'm not going to do this, but 0.0132 or whatever, I can't read this backwards. 0.0123. So you can see all the different contributions from all the different categories. And that's important to know because there will be times where it's, maybe it's, why was this distribution? Why was it rejected? You can go back and you say, oh, these two categories in particular were so far off from what we expected that it doesn't fit because of those two categories. Are you guys with me on that? So you can actually find the contributions. And really what's more important is the relative contributions, not so much the absolute numbers. Okay, so I hope this has been a pretty smooth run through. I know I failed to explain things clearly at certain times, but hopefully in the end, we're able to piece it together. So there are some homework problems tonight, which are going to give you some good practice with your goodness of fit. You can practice doing that on your calculator. The caveat I wanted to say as far as being able to do this stuff on your calculator is, remember, I've mentioned a few times, the AP test is designed to be done without a calculator. So your chi-square tests are primarily going to be conceptual ones, or here is the output of a chi-square test, interpret the results, or you kind of get the idea. So you're not going to necessarily be sitting there doing and performing a chi-square test. Okay.
But
You never know. You want to be prepared, and knowing the full process will set you up for those conceptual questions. All right, I've definitely talked enough for today. Let me know if you still have questions on anything we talked about, but besides that, have a wonderful day and I'll see you tomorrow.